Alright, here we have a famous function in mathematics. So the Euler's phi function, or the totient function, to know what phi sub n is just going to be the number of divisors that are less than n. So in other words, here's some common ones. To find phi of 6, you list all the numbers between 1 and 6, but you don't include 6. And then you just figure out which ones do not share a factor in common with 6. Well, 1 has, 1 you keep because it has GCD of 1. 2 and 3 won't work because 6 has a divisor of 2 and has a divisor of 3. 4 also doesn't work because 4 and 6 have a common prime in common of 2. 5 and 6 don't share a common prime, so we get that that's equal to 2. On the other hand, let's look at a number like 7. List out the numbers 1 through 6. Now, how many of these share a prime with 7? Well, in fact, none of these share a prime with 7, so we get 6. In fact, if you see for any prime, you're going to get p minus 1. Let's look at one more composite number. Let's look at, say, 15. So I'm going to look at the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Which of these have a prime in common with 5? Well, 1 doesn't have any primes, so we're done. 2 does not share a prime with 15. 3 does, though. 3 divides both 15 and 3. 4 has nothing in common. 5 has a 5 in common. 6 has a 3 in common. 7 is relatively prime. 8 is relatively prime. 9 and 15 share 3. 10 and 15 share 5. 11 and 15 are relatively prime. 12 and 15 share 3. 13 and 15 are relatively prime, and so is 14. So we get 1, 2, 3, 4, 5, 6, 7, 8 box things. So we get a grand total of 8. That's the phi function. Here's some more examples. I said for primes, you just do p minus 1. Running through some of those. Right, so this notation, 1, 4 means GCD of 1, 4 equals 1. So it has GC, the phi of 4 is 2, since you have 4 and 3 are relatively prime to 4. That should be a 3, 4, but 2, 4 is not. All right, so 9 is 6 because 3 and 6 are no good, but these numbers are coprime, so we get 6. All right, so here's a theorem. If you have a cyclic group of order n, there are phi of n elements that generate it. So in other words, what we're saying is that phi of 6 equals 2 is what we said earlier. That means that Z6 has 2 generators, and in fact it does. It can be generated by 1, and it can be generated by 5. Z9, phi of 9 is equal to 6. That means it should have 6 generators, and you see it does. Z9 can be generated by 1, 2. Why is that? Because you get 2, 4, 6, 8, 1, 3. I'm adding 2 each time, mod 9, 7, 0. You get all the elements. 3 won't work, but 4 will work. 5, 6 won't work. 7 will work, and 8 will work. So that's what this theorem is saying. So let a little g be a generator, and it has order n. That generators. Every element has the form g to the k for some integer k. That's just what it means. So every generator can be written as g to the k for some integer k. All right. So we just need to figure out which k are going to be. And so we're going to prove that we have a generator here if and only if the GCD is 1. What we can do is first of all, suppose that the GCD is 1. Then, there should be space there. We're going to let m be the smallest numbers. Then let m be the smallest positive integer such that g to the m is in gk. By a previous theorem, we know that m divides k. So this is the theorem. It's about subgroups of cyclic groups. And this video is on my channel. Go free to look it up. It basically says that every subgroup of a cyclic group is itself cyclic. So the identity is in there. We know that m is the smallest, so m has to divide n. So m divides k and m divides n. Right? Why does m divide k? Because m is in there. Why does m divide n? Well, because all right, there's a typo there. That should be E equals g to the n, because cyclic of order n. That should be an element of g to the m. So I'm looking at two cyclic subgroups here, g to the k, and I'm also looking at g to the m. So that gives me the two divisions I need. M divides k and m divides n. And we know by assumption that the GCD of n and k is 1. So n and k have no primes in common, but all the primes in m divide k, and all the primes in m also divide n and k have no primes in common. So if all the primes in m are in k, and all the primes in m are in n, and these two have no in common, that means that g equals g sub 1 equals g to the k, which means that g to the k is a generator. So whenever we have that the GCD is equals 1, we get a generator. So we have this basically gives us an equality. We know that the number of generators, they're at least the number of generators is at least phi sub n, because every time you get a phi sub n, you get a generator. Every time you get something that's co-prime, you get generated. Now use the other direction by using positive. We're going to prove that if the GCD is bigger than 1, we're not going to generate the entire group. We're going to suppose that GCD is equal to d. We're going to let m equal to n divided by it. And that's got to be less than n, because I'm divisible. Also, though, n has to divide m times k. Why is this? Because m sub k is equal to n divided by d. If I multiply by k, I can go more. But k is equal to d times l, where l is some integer. Why is that? Because d is a divisor of k. So I end up with something like that. And so I get just nl. So mk is equal to ml. So n has to divide mk because I can write mk as n times something. In this case, I'm calling it l. So that's why n divides it. Now, since n divides mk, I get that this is equal to the identity, because I get that g to the mk equals g to the nl equals g to the nl, which equals the identity L, which equals just the identity. That's an L. So then the order of gk is less than or equal to m, because if I raise it to the mth power, I'm going to get the identity. But I know that m is strictly less than n. That means that the order is less than n, so what I get is that g to the k can't give me the entire group because it's less than n. It means that, and that proves the result. So this says that that the GCD is equal to 1 if and only if g to the k generates. The GCD of n and k is equal to 1 if and only if g sub k generates. But how do you get, how many things have GCD of nk equal to 1? For how many k is GCD of nk equal to 1? That's exactly the Euler phi function. Example. Oh, shoot. Sorry, my computer just went. P of 2 equals 1, so every element of the generator. Every element of every cyclic group of order 3 has 2 cyclic group of order 4 has 2 generators. Every cyclic group of order 5 has 4 generators. This 4, if you have this of order 4, then you get that g to the 1 and g to the 3 are going to be generators. That's it. We're done. Thanks.